Good afternoon, everyone, and thank you for joining us for today's webinar. Today's webinar is entitled Identifying Seized Drugs, an application of mass spectral library searching. We have the privilege of two subject matter experts today. Our first subject matter expert is Arun Moorthy. He is a mathematical statistician in the National Institute of Standards and Technology, NIST Mass Spectrometry Data Center. He works on developing, analyzing, and improving mass spectral library search algorithms. His primary area of focus is characterizing uncertainty in compound identifications made using EI mass spectral library searching. Our second presenter today is Gary Mallard. He was at NIST for 31 years working in fire and chemical kinetics research, chemical kinetics, mass spectrometric, and retention index databases. He was the first editor of the NIST Chemistry Webbook and the group leader for the Chemical Reference Data Group, which produced both the NIST Chemistry Webbook and the NIST Mass Spectral Database. He was on the team led by Steve Stein, who worked on the development of AMDIS and developed extensive training material for AMDIS. After retiring from NIST, he went to the Organization for the Prohibition of Chemical Weapons as head of the OPCW laboratory. And after 3.5 years at the OPCW, he again retired and is now a consultant working with NIST on methods to improve AMDIS, the NIST Mass Spectral Database, and tools for forensic analysis, as well as other clients on GCMS analysis. We've got a very exciting presentation as well as a demo towards the end. Without further ado, I would like to hand the microphone over to Arun Moorthy and Gary Mallard.
Hello, can you guys hear us all right? All right, well, thank you. We still haven't had our
audio sounds great.
Okay, here we go. All right, well, welcome all to our webinar. Yeah, it's great to see so many people from all over the world. I know that it's a lunch webinar for those of us on the northeast of North America, but or the east coast of North America. But the rest of you, great. Thank you for joining us. As Josh mentioned, today our talk will be primarily about identifying seized drugs with mass spec library searching, and in particular about a new method that we're excited about called the hybrid search. So one second, here we go. So the objective of this webinar is really to introduce everyone to the hybrid search, but before one can do that, you really need to have a basic understanding of mass spectral library searching in general, understanding some of the limitations of conventional library searching and what we're able to do now with the hybrid search as an alternative search system. And one of the exciting things Gary will be talking about is applying the hybrid search for, in particular, fentanyl identification related to the newly released federal regulations around fentanyl analogs in the United States. So with that, let's get started talking about mass spectral library searching. First, one needs to have an appreciation for what mass spectrometry is and what the data that we're looking at is like. So here I have an example of a mass spectrum for TCP. What you see here is, and let me pull on my pointer, or there it is. Yep, here we go. We've got a molecular ion for TCP. So what happens in mass spectrometry is you ionize a molecule, and the mass to charge ratio is recorded in what we refer to as a mass spectrum. This molecular ion may further fragment, maybe a single fragment, maybe two fragments, maybe three fragments. There may be rearrangements, there may be reactions between these fragment ions, but all of this information gets recorded in the mass spectrum. In particular, it's the intensity of these fragment ions of the molecule. And in that and this is something that we want to point out, is that this is structural information that is captured in the mass spectrum. It may often seem like there's randomness, but there really isn't. This is chemical information, structural information. The other thing to point out is that the mass spectrum records the intensity of fragment ions, but there are neutral losses every time there's fragmentation as well. And that information can be leveraged further, and this is something that we'll point out with the hybrid search. So sorry, let me go back quickly to the last slide. Here's what I wanted to point out. So as I mentioned, the mass spectrum is strongly correlated to our structural information. That said, given structural information, it is very difficult to predict the mass spectrum because, as I had mentioned, there are several opportunities for fragmentation, rearrangements, reactions, and so coming up with the spectrum for a given structure is not easy. Even harder is, given a spectrum, backing out what the structure may have been. And this is really the motivation behind mass spectral library searching. And the principle is essentially, and let me move this pointer. The principle is that if I've got a library of spectra or reference data, I can use my experimental, or I can compare my experimental data to that reference data using some sort of search algorithm and generate potential structural information about that experimental spectrum. And that's basically mass spectral library searching. So without further ado, let me go to a couple of examples. So here I have a screen capture from NIST MS Search 2.3. My layout may not be the same as what you have. In fact, I think in the demo later, you'll notice that even Gary and I use very different layouts. And it really is a customizable platform, and it's important to customize it in a way that allows you to interpret your results as best you can. So what I have here is an experimental spectrum for an unknown, and I've searched it against the NIST library using a simple similarity search. What you see here is there's significant spectral similarity between our experimental spectrum and our library proposal 1. If I go one step further and look at the second hit, you notice it's very dissimilar. We consider this the ideal scenario. You have a fairly unique query spectrum that you match very well with one thing in the library and nothing else. And so you can identify the experimental spectrum as our first hit with fairly high confidence. And you're right, this is the ideal scenario, and I think when we last ran overall or global studies, we saw that this occurs about 70% of the time. The second example I show you, again, we have good spectral similarity between our experimental spectrum and our library spectrum, or our first proposal from the library hit list. And again, this is a good situation, kind of. If I look at the second hit, I also get very good spectral similarity. Further, if I look at the third hit, I get very good spectral similarity. And so this scenario is also quite common, and it's a good spectrum, but unfortunately it's not identifiable with confidence. You can get a good class identification, and in fact, it's nice to look at some of the structures and see the structural similarity, but one would not be able to identify this compound independently just using mass spectral library searching. You would only really be able to get what we call class identification. So right, the glass half full approach is saying I get good class identification. The glass half empty perspective is that I can't identify this spectrum with mass spectral library searching alone. And now I want to show you a third situation where the first hit that the search algorithm promotes already is very dissimilar with the library spectrum. And this has pros and cons. The glass half full is we're not going to misidentify this experimental spectrum, the glass half empty is we can't identify it at all. And, and looking at the structures here, you'll notice there's a lot of structural diversity, and so we have nothing from this query spectrum as of now. And so this is actually one of the examples Gary will go through where the hybrid search gives us a lot of beneficial information. So for the next couple of slides, I just want to review, basically provide you a general framework of what happens in mass spectral library searching. So we have an unknown, an experimental spectrum. Step 0, as I call it, is you have to obtain a library. This is imperative to any library search algorithm. We require a library, but in particular, a good library. One with high quality spectra representative of compounds that we're interested in. So here I have an example of a very small library, but at least if you look carefully, you may notice that there's a representative spectra somewhere in here. Step 1, after you've got your library and your unknown, is you've got to come up with a way of converting the spectra to a format that the computer can understand. And Gary will go over this in much finer detail, but essentially we've got to create a vector that represents the information in our spectrum. The next step is to compute some type of similarity. In the examples I'd shown previously, it was very clear to the eye when two spectra were similar. Of course, computers are not looking at these spectra as pictures, and so we have to come up with a numerical measure of similarity. And here I just call it, a generic function, but we'll talk about the specific functions going on in this talk. And then the last step of mass spectral library searching is interpreting your results. In that previous example, we looked at the hit list, we looked at the structures in the hit list, we looked at the spectra in the hit list. All of this information has to be used in deciding on an identification, and more importantly, the confidence in that identification. So in this talk, we're talking about algorithm development with mass spectral library searching, which is really only steps 1 and 2. Step 0 and step 3 are manual things that are done either before one starts library searching or after one generates a hit list. And so I guess with that, this is a good opportunity to move on to Gary to explain a little bit more of the nuts and bolts of encoding and similarity.
Okay, come along. Okay, we're going to talk about encoding spectra. How do we take something that looks like this, which comes out of the instrument? Oh, that's right. How do we take something that looks like this, which comes out of the instrument, and put it into a format that we can use mathematically? Well, let's start over here. First of all, we look at M over Z and intensity pairs, and we have a series of these. And we can take those and convert them to a numeric vector. And when we do that, what we get is a vector that basically has as many dimensions as we're going to have in our total number of masses. And that number, in most cases, goes up much, much higher than this. But we start at 1, and we look at the intensity of 1, and there's nothing there. So it's 0, and at 12, at 2, it was 12, and so on. So this becomes our vector. This is our encoding of the data. And then what we do with this is important. But before we can go forward, we have to realize that there's something important missing. There is a lot of variation even within data for the same compound. And the spectrum of a compound may change with small changes in the instrument, changes in temperature of the ion source, condition of the ionizer. And we also may be taking data from different kinds of instruments to compare to our own instrument because we're looking at things in a library. So if we're going to compare all of this, we have to take this variation into account. Let me show you an example of what I'm talking about here. Here's a heroin spectra, and there's 4 different spectra here. And what you see, all of these are legitimate spectra of heroin. But what you see in the case of these things is that the 43 peak goes from sort of being half of the largest peak to being the largest peak. So there's a lot of variation there. If you look at all of these peaks, there's variation. But each of these, we would like our algorithm to identify each of these as a heroin spectrum, because they all came from a heroin molecule. And to do that, we have to change the encoding. And we have to take into account this variation. So instead of the intensities, QI and LI, we use a scaled intensity at each mass to reduce the variation. So we basically have some new QI hat. It's equal to QI to the P, and then for the library, we have the same transformation. And in this particular case, P is something less than zero, something greater than 0 and less than or equal to 1. And then the resulting spectra are rescaled, so the largest peak is still equal to 1,000 or 100, whatever your base is. Now, with that in mind, let's look at what happens. Here's 2 of our heroin spectra. Here's one and another. These are the heroin spectra that you would get out of the instrument. Let me just focus briefly on the 43 peak. Here the 43 peak is 100%, which is what we call the base peak, and here it's 50%. So there's a 2-to-1 ratio here. Once we've scaled these things, the ratio between the peaks is more like 4-to-3. We've reduced the variation between these two. The other thing that's very important to realize is the effect of this scaling on some of these smaller peaks. In this particular case, this 146 is only about 15%. By the time we've scaled it, it's closer to 50%, which basically means that we're increasing the importance of the smaller peaks. Now, why do we do that? Well, we do that for a very simple reason. The presence or absence of a peak is much more important than its absolute intensity. We also want to reduce the variation intensity between 2 spectra. And both of those you could see in that previous slide. We reduce the variation between the spectra, and we enhance the smaller peaks. And doing that, we think we have a better shot at getting spectra to compare, and also not to overemphasize some of the larger peaks. There's other aspects of encoding techniques, and we really don't have time to go into all of them. But one of the most important is scaling the intensity as a function of the fragment ion mass, which we have to do in identity search. This basically makes the higher mass peaks count more than the lower mass peaks, because they're more important for identity. And then something we are going to talk about a little bit is indexing the vector by neutral loss rather than the fragment ion. And that's neutral loss searching. Well, that's sort of, most of these ideas you've probably heard of. You may or may not have encountered neutral loss searching. Let me just very briefly talk about what that really means. Here's a spectrum of TCP. This is the spectrum that you would normally see.
Excuse me.
It's a spectrum where there's a molecular ion here, we're not showing the structure of, and then there are the individual fragments, they're in red, and then there are the little black pieces that are the neutral losses. And so the neutral loss is a 43 here. That's just the difference between 249 and 206. And the neutral loss here is 84 and 152. And we try to emphasize here that the neutral losses may be in 2 steps. They may not occur all at once. Now, at first glance, this looks like, well, all you've done is subtract 249 from everything. That's not really much. But as we're going to see in a little bit, that makes a huge difference in certain kinds of searching. Is this you?
Yep, sure.
Okay, now we're going to go back to Arun to discuss how you measure similarity.
Thanks, Gary. And actually, one of the things that I didn't point out in our overall scheme of mass spectral library searching is how interconnected encoding and similarity and interpretation all are. The way one encodes will affect the way one measures similarity. The way one measures similarity or outputs their results from similarity will affect the way they interpret their results. So when we talk about spectral similarity, we're really talking about a numerical measure of similarity between a pair of spectra. And you've probably often heard the term match factor, and this is ubiquitous, I guess, now in mass spectral library searching, but it's a numerical representation of the similarity between two spectra. And I'm going to talk about really our primary function, and other search algorithms may use different measures of similarity, but our primary measure of similarity is what is called the modified or squared cosine similarity. And what I highlight here as S is our simple match factor, or a match factor using our standard encoding, so square root intensity, no mass scaling or neutral loss scaling or anything like that. So this is our simple match factor. What you'll notice is we have the intensity of our query, which is Q, multiplied by our intensity of our library, and then in general this is a highly nonlinear function that evaluates between 0 and 1, and then we have a constant C, which for historic purposes is 999. And so when you have two very similar spectra, or in fact when you have two identical spectra, this simple match factor will evaluate to 999. And when you have two completely, orthogonal spectra, one would expect this to evaluate to 0. So rather than overanalyze this equation, let's look at a couple of examples. Here I've got two spectra for fentanyl. Here again, what I really want you to correlate is your intuition of spectral similarity and our measure of match factor. And so here, I think this is a fairly intuitive, similar, or calling these two spectra similar is fairly intuitive, and our match factor represents that as well, reflects that with a match factor of 972. A second example, well, we've got two things that, again, intuitively are not at all similar, and we capture that with our match factor of 35. And I want to point out that the structures here are very different, and so as I had mentioned earlier, the mass spectrum is supposed to be reflective of the structural or substructural components of our initial molecules, and so one would expect that two things that are very different will have very different match factors, or a very low match factor, sorry. In this example, this is an interesting one where there's something about it that looks intuitively similar and yet also dissimilar. And of course, this is kind of captured in our match factor. Our simple match factor is only 346. Going over and looking at the structures, you see that they are, in fact, similar structures. And so this is kind of the question or the motivation behind, maybe re-looking at spectral similarity, or more importantly, re-looking at the way we encode our information. So Gary had mentioned earlier the idea of neutral loss matching. So if we look at these two spectra, the exact same spectra by neutral loss, we notice now that there is, again, a lot of similarity now in the high mass peaks, and the dissimilarity comes in these low mass peaks, and we get a neutral match factor. So this is the same match factor computation now, instead using neutral loss as our encoding scheme, of 764, which is a lot higher than, of course, the 300 or so. And so there's an obvious or natural question that comes here. Can we create the best of both of these search modes? And if you've been paying attention to the talk, you're probably not surprised to hear that yes, we can. And that is the hybrid similarity search. The way the hybrid search works is we allow for peaks from our library spectrum to match our query by fragment ion matching. So this is just at the same mass values, but also the peaks that didn't match, but did match via neutral loss, we allow those to shift by a mass shift that's equal to the molecular weight difference between our query and library compounds. So in this case, and in fact, this should be a -14. We allow our fragment here to shift by that delta mass value. And so now if we compute match factors using these blue and pink peaks rather than the original blue and gray peaks, we get a huge elevation in score, 963. And this will, of course, in fact, will affect the way we interpret our results, because this will be promoted in our hit list. So just to summarize, and this is, I promise, our last math slide, we haven't really done anything with the hybrid similarity search short of changing the way we look at our spectra. We allow for structural similarities to be better captured by using this hybrid similarity routine. To summarize the routine, and again, the objective of the routine and what we're accomplishing is we're combining fragment ion and neutral loss matching when computing spectral similarities. So the way this is done, first we have to come up with this parameter called delta mass, which is the molecular weight difference between our query and library compounds. Then when we're building our what we call a hybrid spectrum of our library spectrum, we compare each query peak either to the MZ value, at the direct MZ value, but then also at MZ plus delta mass. And what this tells us, if we match by step one, is that those are the two compounds likely form the same fragment ion. And then if they match by MZ plus delta mass, this suggests that the compounds form the same neutral loss. And so what this is able to do is generate high spectral similarity scores between compounds that differ by the insertion, deletion, or replacement of a single chemical moiety. That doesn't greatly affect fragmentation. And so now I guess I've hopefully convinced you that we have come up with a new way of measuring similarity that does a good job, but what you probably want to see is how it works in searches. And so I will pass it on to Gary to give you a couple of good examples.
We wanted to focus on identifying fentanyl analogs in this because there's a new recent federal regulation that basically tells us in chemical terms how we can look at the notion of an analog. And I'm going to go through these things, and I'm going to discuss briefly how these things affect library searching, because you can, even if you don't know what a compound is, you can often identify it as a fentanyl, and you can get a lot of information about where the structural changes have occurred. So let's look at these things, and I'm going to start off with the pieces of the regulation that basically address what happens to the phenylethyl group. Either we change the phenyl group or we put something on the phenylethyl group. These are class A and B changes. In all of these cases, the major fragment is this piece of the molecule back over here. And what we lose is this piece of the molecule here or here. And so our neutral loss is different, but most of the fragmentation in fentanyl goes through this piece of the molecule. And so as long as this piece of the molecule stays the same, we expect to see similar spectra. And if we look at that for for one example, here's an example where we've actually got two changes in the molecule. So this is this is a combination class A and B, and this is a simple match. This is not the hybrid match. But what we're looking at here are match factors that are in the 800s. This compound is not in the library we're searching, so we haven't identified the compound. But what we have done is almost all of our top hits are fentanyls. And so we have a lot of information that says this is a fentanyl, even without the hybrid search. We would get even more information if we use the hybrid search. But let's go on and look at some of the other classes. The other class is substitution in or on the pyridine ring. Oh yes, I got to move this guy. And so this is a substitution here to give the 3-methylfentanyl, and a substitution here to give what is called carfentanil. Now, the spectrum of both of these compounds are probably in your library, but I'm going to simulate them not being in your library by simply ignoring the direct hits and looking at the rest of the hit list. And let's see what that looks like. In the case of carfentanil, here's the first of the fentanyls that it finds, and oh yes, and what you see is a simple match factor for this of 359, a hybrid match factor of 707. This is the difference here is huge. You would have never seen the fentanyl spectrum at all if you had not done the hybrid search, because it would have been too far down on the hit list. If we use the hybrid search, not only do we get a higher match factor, but probably the more important thing is that we get a whole series of compounds that look like fentanyl. They're various analogs of fentanyl, which is basically telling us that the structure that we have, that the spectrum that we have submitted arose from a fentanyl analog. In the same way, if we have a much simpler change, we just use the methyl, this is the 3-methyl, we see here now the hybrid match factor is extraordinarily good. Here's the shift that Arun was talking about, where we shift we show the shifts of the library spectrum to match up with the submitted spectrum. In this case, it's a shift of 14. And again, notice the very, very large number of fentanyl-like structures. So again, even though we don't, I'm emulating a situation here where we don't have this. You'll notice this is the second hit. The first one was this compound itself. But even in this case, we get a very high number of hits. And what's perhaps less obvious is we have a delta mass here that basically tells us what the molecular weight of the resulting compound is. If we look at the replacement of the aniline ring, this is a more difficult result, and we have several different cases of this. And when we do that, I wanted to show it to you in a slightly different way. Here's what we do with the normal search. If we search the spectrum of this compound in the normal search, this compound is not in the database that I'm searching. And so this is what we get. We do get one thing that looks maybe like a fentanyl. It is like a fentanyl, but it has a match factor of 660. When we do the hybrid search, we get a match factor of 988, but even more important than that, we get a very large collection of compounds. As a matter of fact, 14 out of the top 15 in the hit list are fentanyl analogs. This gives us a great deal of confidence that we have identified this unknown spectrum as a fentanyl, not necessarily, and because we don't have the structure in the library, definitely not, have actually identified the compound. But we've gotten a lot of information about it. And I'll go on to the final qualification here, where we have the replacement of the N-propanil, and that's basically a change in this end of the molecule. And these are all very good examples of the hybrid search. And so let me just sort of show you one of them. Here, the normal search for this, which I'm not showing you, had no fentanyls in the top 100 hits. Now, I want you to basically notice that there's a lot of fentanyls in the top hits here. I also want you to notice that in most cases, the change from molecule to molecule is in this piece of the molecule right here. So it's not only indicating that this is a fentanyl, but the hybrid search is pointing us to exactly where the change in the molecule is. And one thing that's sort of a bonus, and you don't often get, is that this particular piece, this particular thing, which isn't really a fentanyl, but looks a little bit like one, has this furanyl compound, and that's exactly what's over here, and that's what gives rise to this 95 peak. So in effect here, we've proven to ourselves that it's a fentanyl. If we examine the hit list carefully, we know where the change was, and we've at least got a hint as to what the change looks like. So this is what we are hoping to be able to convince you is a good tool for you to use. And we're going to go now to a live demo, and we're actually going to pull one spectrum up. Share my screen.
Yep.
Oh, share, sorry. Okay. Now I'm going to go and I'm going to search, I'm going to find a particular data file. We've preloaded, we've got one set up over here. It's an unknown, and if you really were paying attention at the beginning of the talk, you will remember this unknown. We're going to import it. You may have forgotten, but this was the very first thing that Arun showed you. And I'm going to do, initially I'm going to do a search. I'm going to do I'm going to do an identity search on this thing. So I'm going to see if there's anything in the main library that shows what this thing is. And so I'm going to do a library search here. And what I get is a maximum match factor of 568. And I get nothing that looks even remotely interesting. And if I was suspecting that this was a fentanyl, I would say, this is essentially useless. And what I have proven to myself is that the compound isn't in the library, or at least the spectrum isn't in the library. Now, let's now do a hybrid search. So I go to similarity and I go to hybrid, and I'm going to just tell the thing to figure out what the mass of this is. And there's some algorithms built into the program that figures out what the mass is. And so we're going to do a library search, and it does this. And lo and behold, it really amounts to no real additional information. And so you ask yourself, well, why are these people telling us that this particular thing is good? Let me point out to you a little down here in this little corner down here is the mass that the compound used. And remember when we talked about neutral loss, what we said is that we were subtracting the molecular weight of the compound. It looks sort of silly in the example that I did because I just subtracted 249 from everything. But in order to get the proper neutral losses, I need to know the molecular weight of the compound to start with. And in this particular case, the algorithm is guessing 402. Well, if you know a lot about fentanyl spectra, you know that mostly you have a loss of 91 as your major loss for a lot of fentanyls. And so that's usually your first and one of your larger ions. And you look at this and you say, well, wait a minute, if I add 91 to this, I don't get 402, I get 403.
404.
404. Oh, thank you. Okay. Yes, if you add 91 and do it correctly, you get 404. So I'm going to go up here and I'm going to override the nominal mass. And since this is a demo, I've already written that number in there. That's 404. And so now I'm going to redo this search, and I'm going to force the program to use the 404. And I do a library search for this thing. And suddenly, I get a very large number of fentanyls. I get a much higher match factor. But probably the most important thing I get is something that gives me a certain amount of confidence that I'm really dealing with a fentanyl. And when I look at some of these things, I look at this particular, and by the way, I'm looking at these things as structures. You can also look at these things as names. And if you look at it as names, it tells you what the delta mass was from each one of these. And so I'll go to this one. This one's sort of interesting, cyclopentylfentanyl. And I choose that to be interesting because I have a sense that I know what 28 is. 28 is 2 methylene groups. And so I could say, well, I could substitute 2 of these hydrogens by methyls, and I would get something that would have the right molecular weight. I don't have that in my library, or I would have found it. But I could get anything that got me that kind of thing on the side over here. And maybe, although I think if we spend some time looking at these structures carefully, I might see that I could put the methyl group someplace else. But for the most part, what you see here is you don't see, in our search here, you don't see changes in this part of the molecule. You see changes out here in the molecule, which makes you think that whatever change is going to occur is out here. Well, it turns out that it's not dimethylfentanyl, and I will show you what it really is. I will add the most recent SWIG drug library. I've just been searching the NIST main library. If I add the SWIG drug library and do this same hybrid search, I find a very high match factor, and it's for this compound. And this, in fact, is the compound that we gave it the spectrum of. Now, the problem with what I did was that you have to know a lot, and so if you don't have a good idea of the molecular weight, you can go fairly far afield in this, and you might spend a lot of time hunting around for the molecular weight. We've recognized that, and Arun has started work on a very interesting tool that he's going to briefly discuss with you.
All right, thank you, Gary. So I'm going to quickly switch over to that tool. And so what I have here is called the NIST molecular weight predictor. This is very much a prototype. We're really just getting started. But one of the things you've probably observed through all the examples that Gary showed you, and also the ones that I showed, is that when you use the hybrid search, you get a good score elevation. That is, the score using the hybrid search, it's much greater than it was using the regular search. And so I tried to leverage that and scan through several molecular weights and see if I can get the correct see if I can get a maximum score elevation at the correct molecular weight. So here I have an example of this is a pre-thought out example of fentanyl, and I searched it against the SWIG drug library, ranging between assumed molecular weights of 282 and 443. And I clicked this predict molecular weight thing, and I don't know if you can see it here, but there's a progress bar. All right, and so and as I said, this is a prototype, so we're testing several methods. In one method, in both methods, we get the correct molecular weight of fentanyl, 336. One method with a very high confidence, the other method with a lower confidence. I won't go into too many details about how these methods are computed for now, but again, I just want to point out this is a work in progress. Now, this was not the example Gary talked about, so I'll quickly show you how Gary's example does. And again, I'm going to search, but this is the old SWIG drug library, so this compound is not in my search library. But if I again quickly search it against the old SWIG drug library, I can get a plot like this, which shows how score is elevated over a range of assumed molecular weights. And I'm trying to identify a maximum there, or take from that information something that points to what the molecular weight may be. And so give it another second or so, and here we go. So again, two methods. One method gets us the right molecular weight, the second method not so much. So again, this is a work in progress, but we're making grounds, and this is, of course, right now, as of now, the real big limitation with the hybrid search. In fact, we've got several questions from people where once they modify their molecular weight, they see all the incredible value of the hybrid search that we've highlighted thus far, but it really does rely on getting the correct molecular weight with your unknown. All right, so with that, maybe Josh, we can switch back to our slide deck. Great. So our slide deck has not reappeared yet. But I can start talking about what the next slide is, which is really just a summary. There are two manuscripts at present that describe the hybrid search, one by my colleague Megan Burke about applying the hybrid search for proteomics, and then I have a manuscript published late last year about, again, analyzing forensics compounds. And then the last thing I want to point out is that the software was developed for use with NIST 17, but it can be used with any mass spectral library in NIST format, and so if you've got a custom library that you like to use in your lab, then you can still convert it to NIST format and try to use the hybrid search. For more information about the stuff that we've done, please visit www.chemdata.nist.gov.
Yes, you might need to go back to the application. It might be at the bottom of your screen since you were screen sharing, but we do have the slides up for the audience.
People can see our screen is blank now. Okay, good. Well, we can't see it, but I trust that it's there, and so yeah, that link that you can follow that, and we'll we'll be happy to take any questions going forward. And you'll notice on the
All
next
right, we
slide,
do have that last slide up with your contact information, so that is there. We did have some questions that came in, so we'll just jump right into it. The first one came in from Wayne Morris. He's asking, what do you consider an acceptable quality of match between unknown mass spec and library mass spec?
There's not really a good answer to that. What can be said is that once you get below about 800, it's not very good. And so, but if you remember the first slide that Arun showed, where we were comparing sets of spectra, and he showed the very first data, the very first match was very good, and the next one was very bad. And we didn't have time to discuss it within the framework of this meeting, of this talk. But there actually is there's a numerical method that looks at the difference between the first and the second hit, and that gives you a probability that you've gotten the right answer, and that probability increases as the distance between them goes up, and that was reflected in the third spectra, in the second set of spectra that Arun showed you, where all three of the top three hits, which were three different compounds, had very, very good match factors. That's why I say there's not an answer to that. And that's true of a lot of things. You can look at, for example, pentalone to do something within the forensic community. And there's a compound called 2,3-pentalone, which is a very close isomer of it, but I don't know what the relative effectiveness is, or whether 2,3-pentalone is regulated or not. But the spectra are so similar that you really can't tell them apart. You have to use some other methodology, such as retention data, or for a lot of forensic labs, they also do IR. But you need a second technique for some things. For other things, I think if you've got a match factor in the 850s or above.
All right, thank you so much, Gary. Next question we have, what do you think about comparing intensity of fragment versus intensity of base peak to the ratios from library or known standard mass spectra?
Do you mind if I take this, Gary?
No, go ahead.
I think actually that's a great idea. And one of the things that we talked about was how encoding changes our interpretation, or sorry, our encoding changes our measure of similarity, and our measure of similarity changes our interpretation. And so it's possible that instead of using well, so right now all the peaks are relative to the base peak, but using the ratio instead of the values of the intensities may in fact be useful. So that is something to look into. I don't know. It's possible that someone has looked into this already before.
All right, next question we have. Recently we've been seeing a base peak of 93 in fentanyls and its analog. Sometimes the sample is extracted in 1N-HCl CHCl3, and sometimes is just put into MEOH. Is this ion from the source rearrangement or from the column bleeding?
The right way to answer that question is to not look at the spectrum, but to look at the ion's time history. And if you look at the time history of the ion of the 93, if it's part of the compound, it will also have exactly the same time history as some of your other ions, as some of your more principal ions. But I don't know that I can actually answer that question directly. I mean, one thing that we would certainly be willing to do is if you've got a data file and you want to send it to us, we can look at the data file and
All
try
right,
to
not a
get back
problem
to
at
you
all.
and
We
maybe
can
also get back to the
move
group as a
on to
whole
the next question.
with perhaps a
Is the
better
hybrid
answer. But
search
I don't know
option
the answer.
available on older versions of the NIST library?
No, it's actually new with MS Search 2.3 and with NIST 17. You may be able to use old libraries, but you've got to re-index
Okay, that
your
kind of brings us
Spectra.
into
And
the
when you
next
go to NIST
question.
MS
This is
Search
only available in
2.3,
MS
and
Search
if you
version 3, which
come
was
across this,
released
we
with
can help you
NIST
re-index
17.
your library.
Can you get a free download of this? And if so, where can they find that?
Yeah, so there is a demo library with MS Search 2.3 available on that website. One of the things, though, we do need to point out, and in fact, we should have highlighted this, the hybrid search is useful if you have similar compounds in your library, right? Remember that example, we couldn't identify one of our unknowns. The idea is that you're able to classify it with confidence if there are other compounds in the library that you can find. And so with the demo library, I can't recall exactly what's in the demo library, and so it won't work nearly as well. But what you may be able to
All
do
right,
is,
next
for
question.
example,
What
download the
about
free Skin
getting
Drug library
molecular weight
and then employ
by
that
CI
with
or
the
derivative
MS
or
search tool.
derivatization?
That would work.
Yeah.
Yeah, that's a good idea. I mean, and if that's a if you run a separate CI experiment, you're going to get the molecular weight of the compound, and then once you do that, then you're guaranteed that when you go back to your EI data, which is richer and more likely to give you structural information than the CI data is, then you can input that molecular weight if the program doesn't automatically get the right one. And so, and that was the example that I showed in the demo. The program didn't get the right one, but I went back and in fact I used a logic based on neutral losses and the assumption that I had a fentanyl.
Next question we have is from Melanie.
To
She's
input
asking,
the
is the
molecular weight.
hybrid
If
searching
you
tool
actually
ever
had external
successful
data, it
without
would even be
knowing the
better. It's
molecular
always
weight
better.
of your unknown?
Yes, a lot of the time it is. As a matter of fact, probably more often than not, it works. And it works because there is an estimator built into the NIST database that is pretty good at getting molecular weights. Where it's not very good at getting them is in things like fentanyl, where there's almost no molecular ion. And as a matter of fact, fentanyl is especially confusing because it'll often give you either an M-1 or M-2 and sometimes an M+1, but they almost never give you a molecular ion. And so the estimation tool that is built into the NIST database doesn't work as well as we'd like it to. And part of the work that Arun's doing is to try to see if we can fix that.
And yeah, just to give a global statistic, I recently did an analysis, and about 75% of the compounds.
All right. We just had a couple of comments that came in regarding Vi's question back with the peak of 93 in the fentanyls and its analogs. Jamie was stating that they are seeing the 93 and it's coming from the CL3, and then Alexandra commented that there's a similar issue with the fluorofentanyls where the ion of interest becomes 111. All right.
Well, just one comment there. If it's coming from the CHCl3, which I assume they're using as a solvent, then um, I I think if someone was using AMDIS on that, it wouldn't get that, because the solvent should, the peak of the ions of the solvent should just be a tail coming down, and they should be, the AMDIS will absolutely deconvolute those, and you won't get a 93. If you're just doing, if you're just looking at the peak alone and not doing background subtraction, that may be what's going on there. But if you're, and that, that may also be being, I mean, that's also sort of an issue, I would think, of your split ratio, because if you're, is it possible that you're not running these things splitless, and therefore you're still getting the solvent coming out at the same time as the fentanyl? Because if you're splitting them, usually the solvent, if you're using a reasonable split ratio, usually the solvent's gone by that time, and you shouldn't be seeing it.
Right. Next question we have, what would you do if the base peak MZ value
I'd be
changes?
interested in getting some more information from people. Huh?
If the base peak MZ. And so actually, Gary talked a bit about that with our heroin examples, where the base peak changed from 43 to, I don't remember what the other base peak is. And so we tried to account for that with the encoding. But that's really our only approach at the moment. The tighter that encoding, the less that variation affects our similarity. But of course, you can imagine that if you overtune that, then you may end up with false identification.
All right, we do have one more question,
So,
but
yeah,
before
that's one of
we
our
pose
things that
that,
we're working on,
just make sure that you
trying
do
to
take
improve
down
our
the
encoding
contact
to
emails there on
capture
your
those
screen for
differences.
both of our presenters, just in case you do have some follow-up questions. We are also recording this entire event, and it will be made available to you by the end of the week. Also, make sure that you stay to the end of today's event. We do have the PDF version of the slide deck from today. That way you can have a hard copy of that downloaded before you leave. So our last question that came in is asking, how can you figure out the molecular weight with chlorinated compound isotope elements?
Well, there's a common definition of what the molecular weight is, and it's the sum of the most common isotopes. And so you basically ignore the 37, and you just add up you just assume chlorine is 35, and that gives you a molecular weight. When you look at the mass spectrum, you'll see a peak at the position where you made the calculation for the 35, and you'll see another peak exactly 2 masses higher if you only have one chlorine. It gets more complicated if you have more chlorines. So the molecular weight calculation in all mass spectrometry is based on the most common ion. And so we use, in all cases, we use the most common ion, and that's what in mass spectrometry is called the nominal mass, and that's what we put inside.
All right, we do have time for one more question. They're asking if you could clarify where do the weights come from in your intensity scaling.
Oh, the 0.5. Oh, you know what? That's done. There is an optimization done, but at present we actually just use 0.5 as our p-value. But the optimization was done, I guess, on an older version of the NIST library to try to maximize the number of correct identifications.
Yeah, there's a paper by Steve Stein, which unfortunately we don't have where we can immediately show it to you, that goes over the way that algorithm was developed, and it's not real critical. You could have used a slightly higher or a slightly lower version, but there's also a certain historic. It goes back to an old Incos algorithm that used 0.5, but it's not super critical.
All right, thank you so much. We are going to go ahead and move into our closing, but obviously the first thing we would like to do is to thank Arun and Gary for their presentation, their research, the live demo today. That was fantastic, and everything that they are doing for the forensic science community. All right. Again, thank you so much to our presenters. We also want to take the time to thank all of our attendees for joining us today. These webinars are just not possible without your attendance and support. So thank you so much for joining us. Before you leave today, we do have a few things for you. The first, obviously, is our participation survey that you have there in the middle of your screen. Simply click on the word here. It will open up a new window for you. And we would definitely appreciate your time in taking that short survey. That does help us provide to you the best webinar experience, just any content, and also the way that we disseminate that content out to you. So if you could take a few moments on that, we would greatly appreciate it. You will see Julian there in the chat pod is plugging some of our social media as well as our website and our podcasts. So make sure that you're following us on social media. Check out our website for all of our at no cost offerings for all of our forensic webinars, events, and activities. And then our Just Science podcast is becoming very popular, so make sure that you check that out as well. Bottom left-hand corner, we have our file share pod that is going to have a PDF version of today's slides in there. So if you want to go ahead and click on that and download that file before you leave today, that way you do have a hard copy. Again, we are recording this. It will be made available to you probably in the next couple of days, definitely by the end of the week. That way you'll have the ability to go back and review anything that was discussed today. Again, thank you, Arun and Gary, for your time and your presentation today. Thank you, everyone, for joining us, and we hope everyone has a great afternoon.